Hi, good morning, everyone. We'll start in probably another 2-3 minutes.
Good morning.
Good morning. If you have anything to discuss meanwhile, we can do that. Yes, people, does anyone want to discuss anything? Okay, so do you guys want me to wait for another 2-3 minutes or shall I start? What do you recommend? Because just two people are here. And I have seen a tendency in especially your batch. I don't want to say this, but yesterday I received a message from Goopy people that nothing is understandable for probably some of you. So you guys don't ask. Those of you who are not asking, perhaps they are writing to Goopy people saying that we cannot comprehend anything. Anyways, that's so it's hard to deal with such people, in my opinion, frankly. Okay, let's wait for another 2-3 minutes. Okay, I'll start at maybe 9 or 2. If you have any questions, do let me know. And I encourage everyone to ask as many questions as you want instead of writing behind, okay, behind the back saying that, okay, I don't discuss or we are not able to understand anything. Ask if you are unable to understand. What's the point of writing at the end of 2 hours? Oh, it went over my head. So that is something which I find very silly. And you are more than free to directly ask Goofy people to change your mentors, and they will do that. Okay, let me be very clear. If you want that another mentor should be arranged for you, just let me know. I will tell them change the mentor for you guys. Okay. because the way you guys write the feedback, it's something beyond my comprehension. Okay, so there are enough people now. I'll start. If you want, you can, if you want to write messages regarding your queries, you can write to me on this Mentor account. Okay, you can write to this Mentor account. Or you can speak up whenever you feel like, okay, you are stuck or you have a question that is bothering you. Okay. All right. Okay, let me just check. Yep. So,
if you write
yes.
the mentor email ID, it will come directly to your inbox, right?
No. I do not have an ID at gooey.in. Okay. So I don't have that. You'll have to discuss with me in the session itself.
No, okay. Like while I'm practicing, if I'm getting something, I'll discuss that in the next class or write to the mentor, which is the easiest way to reach you. I mean, the shortest way to reach you.
To reach me, see, I frankly do not encourage or I will not provide my email IDs as such. So if you want to discuss anything with me, it's better to discuss in the class, because I frankly have a lot of commitments, not just this particular commitment. Okay. This is like my part-time consultancy. Okay. So I have a full-time job and another few consultancies as well. So in the class, I'm available to discuss anything for any duration. However, I do not, I do not intend to provide my email ID as such. I believe there are mentors reserved for this. You have this mentors at the rate something gooey.in, right?
Yes.
So those people also know about the subject and everything, and they typically take care of all these queries. But you are more than welcome to discuss with me in the session itself.
If not in the following day, correct?
I believe, yeah, you can email them directly.
No, Sanatan, if
Yes.
my doubt is coming in the evening, I will discuss with you on the following day. Correct?
In the next day. Obviously, see, nobody is going to be available at that very moment when you have a doubt, right?
Yeah, that's true.
So, you cannot expect a response at that very moment if you are stuck in the evening or let's say stuck at the night.
Anyway,
I hope you get that. I hope you get that. Okay.
Yeah,
even your peers will not be available at that moment. See, I'll be very frank. If I don't want to say this. Okay. I think people have a tendency to assume since they are paying, they have a slave. So I don't want to go that far. I just want to say that, like, no. See, so I'm available for your. See, I'm available for any discussion. Okay, at in the class for any duration. Okay. However, beyond that, do not expect me to. Return to your queries when you are free.
I get you.
All right. And if you have any queries, then write to mentors. I believe they respond within a few, maybe within a few hours. If they don't do that, then you can tell me. I'll write an email to them saying that why are you not responding to the queries of the students?
Okay. So the TAT is 24 to 48 hours.
Oh, all right. I get that. Okay. See, I believe you are intelligent enough also to find your answers in a limited time span. Yes or no? I just type your query on Google.
We'll try to help ourselves. If you are not able to help ourselves, then only we'll reach you, right?
Then I'll be there the next day, right? The next morning, I'm there. So I'll be happy to assist you. Okay. See, okay, obviously I cannot be present at that very moment. If that's what the query is, I'm telling you frankly. See, this is the politest that I can be. Okay. This is okay. Again, I will put it like this. Even though I'm representing Google right now, I don't think any mentor would provide you the direct contact number, even though I did in the past, and that kind of took away a lot of my time during the day.
Oh, okay.
Because everybody contacted me, unlike anything, even in the night at 11:30, 12 o'clock. So it takes a lot of time. And further, like, people will ask without even looking up on Google or let's say any other resource. They directly message you, even if it's a trivial doubt. So that's one of the reasons why I typically don't share my personal ID. Okay, but feel free to contact me if there is a genuine doubt. I'll give you my ID as well. Okay, this is my email ID. I typically respond within half an hour or so, unless I'm super busy. Okay. All right. This is my ID that you can note down in case you want. Okay. Just note down. I'll just rub it off because Govi people might have an issue with it. They have told me explicitly not to do that.
Okay.
But since you asked, I'm sharing it.
Thanks a lot, Sanatan.
No worries. Okay. So this is my surname followed by dot followed by the first name @gmail.com. Okay. All right. Okay. So yesterday we were discussing gradient descent. So as you would recall, it's a technique to find the you can say the roots. By the way, these roots are also called as critical points, okay, of a given function. And which specific critical point I am interested in finding? This particular method, the lowest point. Okay, so I would say this is a method to find, okay, the root for minimizing. I mean, that leads to the minimum. Okay, that leads to the minimum. Okay, that leads to the minimum of the function. Okay, so the idea was this: given a function, if you want to minimize it, let's say this function has some parameters. Maybe say the parameter is say m and c. Okay, let's say these are the parameters. So what you will do is, so if one of the parameters is m, so you will start with some initial values of m and c. Okay, start with some initial values. Okay, and what you will do in the next step is, let's call these initial values as maybe say m0 and c0. The 0 here represents the iteration number. Okay, this 0 on the top, okay, it represents the iteration number. So it's the initial value right now. It's the initial value right now. Let's say I want to get the next value, which is m of 1. Okay, I want to update the slope. Okay, how you can do that is, take the previous value, which is m0, the initial value in this case, and what you do, you subtract the gradient. So this would be the gradient of your function with respect to m, and the gradient has to be computed at the initial value. Okay, the gradient has to be computed at the initial value, and you'll be multiplying a learning rate with it. This is your learning rate. Okay, so you can update m. Okay, similarly, you can update c, and this time you'll be differentiating with c at c0. Okay, so this is your you can say one update. Okay, this is your one update. Let's say I want to do this for many iterations. So I'm going to write this generally. Okay, so let's say if I have m plus 1 updates, or you can say m is the iteration number. Instead of writing it as m, let me write it as say, just a second. Let me write this as say t plus 1. Okay, so t plus 1 will take the previous value m of t, and you are going to compute the gradient at this m of t. You're compute the gradient at m of t. Same thing here. So if you want to find the next update for c, so c, the iteration number is t plus 1, and you're going to take this iteration t. You're subtracting the gradient. You're moving in the opposite direction of the gradient regulated by the learning rate, and this would be ct. Okay, any questions up to this point?
The learning rate will be calculated at m0 constantly.
No, learning rate I'm going to discuss today. Okay. But you can keep the learning rate. So, like the simplest strategy is keep learning rate constant throughout.
Okay. So,
okay. So maybe say eta is say 0.1. Assume. Okay.
Okay.
Or maybe say eta is 0.01. Okay. See, the lower I keep the learning rate, I am guaranteed to converge, right?
Yeah, as you said.
Okay. So
Earlier.
but it will take me more time. But I'm guaranteed to converge. Okay. So assume that you have a small enough learning rate. We will talk about the implications of it. And there are strategies which can help you control this learning rate in an efficient way. We will talk about it today. Okay. But is this part clear? You have these two parameters and you are going to update it. Okay. So in every iteration, you are going to update this. Okay. In every iteration, you are going to follow these two methods. Okay. Basically, these two weight updates, and these are called as gradient weight updates. Okay. These are called as gradient weight updates. Now, this is when you have one feature, right? So assume that you were trying to learn from one feature and the function is linear. So what was the equation? The function that you're trying to learn is linear. So what was the equation J?
mx plus c.
No, that is the prediction equation, mx1 plus c. What is the loss function that we are having? How do we measure the error? This function. What is it that we minimize?
It was
Sum of squared errors?
Yeah.
Sum of squared errors? Yeah. yi minus
y
I hat whole square, right? You can even put any constant outside, it is not going to make any difference. Okay, where yi hat is m times x1 I plus c. So do you understand it now, like how it works? So start with some initial values of m and c and keep on doing this until what will happen? Okay, can you think about it? When would this process stop?
When the slope
Is
comes very near to zero, like
you can
minimum.
stop that. Absolutely right. When this thing becomes zero, what will be the update? Will there be any update in M or C?
No.
No, right? So that is one condition where you can stop. Okay, forget about slope being equal to zero. Can I say that you run it for a fixed number of iterations without caring about what the slope is? Yes or no? I can run this process, say, for 100 iterations without caring about what the slope is, right? It will finish, right? Yes or no?
Yeah.
The process will finish.
Yeah,
you will
somehow.
reach somewhere closer to the minimum. I mean, it's not guaranteed how far you will be. Okay. So if you want to put a more stricter constraint, you can say I am having both the constraints. The number of iterations are say 1 lakh. Okay. But I'm going to say that when the slope is very, very small, I'm going to stop there. Whichever is achieved first, I'll stop there.
Okay.
Yes or no? Whichever is achieved first, I'll stop there.
So the minimum, there is no condition that the minimum is supposed to be zero only. It's maybe
it can be any
0.
number. So think of this function that we took, right? 3x squared plus x. What is the minimum in this equation? Minimum. I want to achieve the function's minimum, and I want to find that value of x that leads me to that minimum. So the value of x is 0, but what is the minimum at that value? 6, right?
Yeah.
So think about it. If I reach to a value which is say 6.000000001, don't you think I still have a good solution?
True.
Okay. So can I say that if I look at the error value, or you can sorry, I'll put it like this. If I look at my function value, so this is, let's say, y hat. Okay. Yeah, you can, sorry, this is my function value, let's say j. Okay. So I'm looking at my function value right now, and I'm at currently iteration, say m. Okay. And I subtract the previous iteration value. Okay. I subtract the previous iteration value, and you can say I'm taking the absolute difference of it. So if I was at, let's say, 6.0000, and this is too small value. Okay. And if I take the difference, can I say that if this difference is smaller than some threshold, I will stop?
Okay.
Does that make sense?
The threshold will be
something that you set, like 10 to the power minus 4 or 10 to the power minus 5, anything of that order. Okay. You can keep it high. If you keep it high, the number of iterations that it will require will be less.
Okay.
Okay. So there is a relationship between the number of iterations. Let's call it as max ITR. there is a relationship with respect to the slope being closer to 0. Okay.
Mhm.
So if the slope is being closer to 0, don't you think these two things are kind of equivalent? The difference in the successive iterations of the error function, if that is very, very small, which means that slope would be very, very small, right? Okay, so these two conditions are kind of equivalent. So what people do is either this or this. Okay. All right. Or you can have a condition that, okay, this is exactly equal to 0 if in case you reach it. Okay, in case you reach it.
Okay.
Okay. But that is unlikely to happen. You will be very close to 0, but see, you have to stop somewhere. You cannot keep on running this for a infinitesimally time, right?
Okay. So the minimum that we were you have mentioned 6, right? So if we were differentiating this that 3x square plus 6, it will come to 6. So that's what we were saying, that the minimum was 6, right?
Correct. So I do not know about this minimum for a generic function, right?
Okay,
I cannot even plot this if you think about it.
Okay.
I want to reach there.
Okay.
I want to reach there. Don't you think, let's say, so I'm saying that, let's say I was at this value. Okay, let's say 6.001 right now. I don't know where the minimum is. Okay, I don't know where the minimum is. Let's say I update it and I reach to a value which is, say, 6.000000000000000 say 9. What is the step size? Very, very small.
Yeah.
So I am saying that you can stop now. Do you realize, like in the last class that we discussed, step sizes were significant in the initial stages? Okay, let me go back and show it to you. Okay. So in the initial few iterations, the step sizes were fairly bigger. Okay, yeah, this is where it would be. Okay, do you see that initial, what is the step size right now? In the first step, when we started at 5.
5, yeah.
Step size is 3 in the very beginning. So you reach to 2. What is the step size after this?
0.8.
1.2. 2 minus 0.8, 1.2.
Yeah, sorry.
And the next is
0.8.
0.8.
From 0.8 to 0.32 you are going. So from 0.8 you are going to 0.32.
0.32.
So what is the difference?
0.48.
0.48. Okay. And if you keep on doing this, do you realize something, that the step size is decreasing?
Yes.
Okay. And why it is decreasing? Because you are reaching closer and closer to the minimum. What happens when you reach at the minimum? The slope becomes what?
0.
And you are actually subtracting this eta times the slope, right? Yes or no? So if eta is a constant and if slope decreases with every step, don't you think the step size would decrease at every step?
Yes.
This number would further decrease at every step, right? So I'm saying that when this step becomes too small, okay, you stop, which means that you are in a position where you have reached the minimum, very, very close to the minimum, because this will only happen when you are closer to the minimum. Yes or no? Does that make sense? Because if you are far away from the minimum, you'll be taking bigger steps. If that is not the case, you try to increase the eta. Okay, you try to increase eta, then you will take a bigger step. But if you take a bigger step, what can happen? You can overshoot the minimum. Okay, so that is why controlling eta is more important. Okay, so if you keep eta to be a constant, you are guaranteed to converge. And if eta is fairly small, you are guaranteed to converge. It will just take more time.
So if the minimum was too far from the slope, we need to do a little more modification on the eta so that we can reach it as soon as we can. But at the same time, we can't go far away.
Too much. Yeah, you can't increase eta too much. See, you know that slope nearing the minimum would be what?
Somewhere around.
Slope nearing the minimum would be what? Closer to 0.
Yeah, closer to 0.
So if you multiply a number which is already a fraction, eta, Eta is a number smaller than 1, right? It's a fraction
Yeah.
between 0 to 1. You are multiplying this number with another number which is closer to, which is closer to 0. This number will further decrease. Okay, so do you realize that now when slope is very, very small, I can still stop? Okay, and if the slope is very small, then you will say that you are at a position of your error function where you are very, very close to the minimum. Okay, you can keep this. This is actually called as tolerance. Okay, the difference that I mentioned. Okay, sorry, just a second. I was writing here. So the difference that I mentioned, this is called as tolerance. Typically, this number can be very, very small. By default, this number is around 10 to the power minus 4. This is, I believe, the default value. But you can change it to even smaller numbers or bigger numbers. Okay. So see, there is like a trade-off. The trade-off is how much time do you have? If you have enough time, you can actually reach to the minimum. Okay, just keep on running it till the time slope becomes exactly equal to 0. Okay. But you may not have that much time. So you have to stop. Okay, because after a while, the step sizes are so small, 10 to the power minus 8, minus 9, minus 10. There is no, reason to continue further. Okay, and I'm going to show you now that first of all, how to control this eta, the learning rate. Okay, how to regulate this. And there are a lot of these strategies. Okay, I'll talk about maybe a couple of them, and you will see all these strategies in the implementation. So the first strategy to regulate the learning rate is this. Okay, why don't I keep learning rate to be very small and let me keep it as a constant? Do you think it will work?
True,
right? Just keep it very small. So this is called as a constant strategy. Another idea is this. So let's say this is your function. Okay, and you know.
So sorry.
Yeah, go on.
Like that constant we were saying, right? Like that we need to keep it around 0 to 1. Like I can put any value like 0.001 or
Yes.
0.001 like that.
Yeah, don't keep higher than 0.5. It will probably diverge.
Okay, so with that, like within that.
Okay, I'll tell you how to know if you will diverge or not. Just a second. Okay. Let me answer that question. Okay.
Sure.
Okay. And this is an IQ question for everyone, not just for you. Okay. Let's say you are on this left-hand side. Okay. Let's say you are on this. You don't know where the minima is, but you know that you're on the left-hand side. Okay. You don't know where the minima is, but you know that, okay, you are on the left-hand side of the minima. Can you say whether you are on the left or the right-hand side? Okay, first of all, you are computing gradient at a certain point, right? Yes or no? Wherever you are computing the gradient at that point. What can you say about the gradient? Can the gradient tell you on which side you are? Are you on the right side of the minimum value or the left side of the minimum value? If you can answer this, then you have understood gradient descent and gradient. The gradient tells you something. Okay, what is the gradient at the lowest value, at the minimum value?
0.
0. Okay, and what is the gradient of any value which is to the right of it?
Negative.
Is it negative or positive? Think.
Positive.
Any gradient value which is to the right of the minimum is positive. All gradients will be positive. And what about when you are on the left? All gradients are negative. So do you think that the sign of the gradient can tell you where you are?
True.
Okay, you are on the right or the left. So the magnitude doesn't tell you anything. Magnitude only tells you how far you are. Because you know that the bigger the magnitude, you are further away from the minimum. Because at minimum, you know, slope is 0 for any function. Okay. Now the question is this. Okay. Now the question is this. Let's say if I keep my eta to be 0.5. Okay. I started with some value and the sign of the gradient changes. So as I update, I can compute the gradient again, right? Let's say I started here. This is where the, you can say the critical point is. Okay. The solution is, the optimal values are. Okay. So if I update and let's say I reach to a value which is here, the gradient sign will change, right? Can you say that you just overshot?
Yes.
Yes.
So what should I do with the learning rate? Reduce it or increase it?
Reduce it.
Reduce it. Okay. So there is this strategy which is called as adaptive. See, constant strategy is very simple. Okay. You keep eta to be fairly small. Okay. So that it never overshoots. Okay. And you keep on running it. Okay. Adaptive strategy says that, okay, my next question is this. Do you want your first step to be bigger or do you want your first step to be smaller?
Bigger.
As
Probably
big
bigger.
as possible, right? Towards the
Yeah.
minimum. Okay. But it should not cross the minimum, right? As big as possible, but it should not cross the minimum. Don't you think that you can figure it out?
Yes.
Just by ensuring that if the gradient sign is changing, okay, if the gradient sign is changing, I know I have overshot. So what should you do to the learning rate? Reduce it. By how much? By how much to reduce? So what adaptive strategy says is this: why don't you divide every time the learning rate by 5 if it overshoots? Okay, divide it by 5 every time it overshoots. Okay, and don't you think in that case learning rate will change? Okay, is that part clear?
So if the gradient was going all of a sudden positive to negative, that time I'll go ahead and
Just reduce the learning rate. Just
Okay.
reduce the learning rate.
Okay. So
Okay, if
like,
it again overshoots, divide it one more time by 5. Okay, and keep on doing this until it doesn't overshoot.
okay, so
And
0.5.
then yes,
Yeah, if the 0.5 was overshooting, I'll go ahead and reduce it to 0.4.
0.1.
If still okay.
0.1.
0.1. Okay, so that.
And then you again see at 0.1 if it overshoots or not. If it overshoots, then you again divide this 0.1 by 5. So you divide it recursively. Okay, you can say recursively till it doesn't overshoot.
Okay.
Yeah. Till it doesn't overshoot. Okay, this is adaptive strategy. Very simple strategy, works nicely. There is this strategy called as invariant scaling, also called as INV scaling. Okay. Now this strategy is very simple. What it says is that why don't you divide the learning rate? So keep learning rate. Okay, do you guys realize I want to keep learning rate as high as possible till the point that it doesn't overshoot? Yes or no?
Yes.
Okay. So my first step should be very, very high. So the idea originally is let me keep my learning rate to be very high. Okay. And then I will reduce it gradually as the time progresses. Okay. So as it overshoots, I'll reduce it. Okay. This strategy says that don't worry about overshooting. Okay. Even if it overshoots, I will reduce the learning rate with some formula. So what it says is this: whatever your eta is, okay, whatever your eta is, whatever your learning rate is, why don't you divide it by the iteration number? Okay, let's say t is the iteration number, and you can add a constant to this iteration number. So t is the iteration number. T is the iteration number. C is let's say a constant that you added. It's a positive constant. Okay, it could be equal to 0 as well. Okay, and there is a power of this. Let's call this power. Okay, and this power is fairly small. Okay, this power is fairly small. Let's say between 0 to 1. This power is fairly small between 0 to 1. Okay, so let me tell you what is happening. Okay, I'll assume C to be 0. I'll assume C to be 0. Power, let's say, is 1 by 2. This is just to demonstrate what will happen. Okay, so in the first iteration, what is the learning rate when t is equal to 1? C is 0, power is half.
Square root of 1. Square root of 1.
So what is square root of 1? 1. Yes or no?
Yeah.
So what would be the initial learning rate? Eta in the first iteration. Okay. So at t equal to 1, so if at t is equal to 0, I started with some initial learning rate. Okay. So in the first step, what is the learning rate? It stays eta. Okay. In the second step, what is the learning rate now? N divided by square root of 2.
Yes.
1.4.
1.414. Do you realize that? Okay. Do you see that eta has reduced? Okay.
Yes.
like next time, what it will become? You are now in square root of 3. Square root of 3 is around, I believe, 1.73. Okay, and you keep on doing this. So every time learning rate is decreasing gradually. Now think of this, even if you are overshooting, don't you think learning rate reduces? So after a while, even if you are diverging, you will come down. Yes or no? Because decrease in the learning rate would be so small, you have to come down. Okay, you will not be over jumping then. Yes or no? Because it will reduce the step size, right? Even if you are diverging, this strategy is actually the default strategy. Okay, in the implementation, this is the default strategy in the implementation. Is that part clear?
So like mostly we were using invariant scaling, like instead of using adaptive, it is
Yes.
more effective, right?
Yeah, invariant scaling is more effective. You don't have to worry about overshooting. Even if it overshoots, it gradually reduces your learning rate. So even if you're diverging, you will come down because learning rate would have reduced after a while.
True.
Okay, so this is the default strategy, and there is another strategy which is called as optimal. Okay, even though this is not optimal. Okay, the name of the strategy is optimal, even though it is not optimal. But what it does, it does the same thing. Okay, it also figures out the learning rate. I mean, with respect to iteration numbers, and it reduces at it's very similar to invariant scaling. It also reduces the learning rate with iteration numbers. Okay, it's very similar to it, but it's not truly optimal. Okay, I don't remember the formula, but it's not truly optimal. I can guarantee you that most of the times, okay, either constant would be the best, a very small constant, you run it for more times, or invariant scaling would be the best. I mean, most of the cases, I would say. Okay, so the people who named it as optimal, it's not truly optimal. Let me tell you this. Okay. All right. So this was about the strategies that are used to regulate eta. I'll show you all of these 4 strategies are there in the implementation, and there is a formula written as well in the implementation. You can check it out what the exact formula is. Okay. So and the idea is still the same. You try to reduce the learning rate in iteration numbers with respect to iteration numbers. Okay. So these were the strategies. Now let us actually try to analyze what gradient descent actually does for a bigger data set.
Can you please go to the previous slide once? Like yes. I was taking a note on it.
No worry. Yeah.
I'm sorry. Like
I was
forgot to
take your time.
Note it down.
I'll share these at the end.
Yeah, like if I'm writing, like I feel little.
That's okay. That's okay. It's good to take notes.
Yeah, like if you're saying something, I used to write it like it looked like a scribbling, but yeah, you can move.
Okay, so the most important fundamental or the takeaway is this: the sign change indicates, okay, the gradient sign change indicates that you have overshot the minimum. This is the, I mean, one of the important questions that you will, I mean, probably see someone asking you if you go to an interview, okay, and if they are asking you about gradient descent, okay. All right. So we just discussed some strategies. Now we are going to analyze what happens when you have a bigger data set. So imagine I have this data set with the D features and the output is Y. Okay. So you're trying to learn a function with respect to these D features and the output is Y. So how many coefficients are we learning?
D plus 1.
So exactly D coefficients and 1 intercept. Okay. Parameters are D plus 1. Okay, so see, even though you are giving me the correct answer because you are thinking about parameters. So, but when I'm like putting it in a certain way, my intention is to ensure that you are able to follow the terminologies correctly. Because interviewer in your interview will probably not accept this answer. Okay, so coefficients are how many?
Coefficients.
Exactly D. Exactly D coefficients. 1 coefficient for every feature, and there is 1 additional intercept, which is theta naught. Okay, and this is the intercept term, which is theta naught. So you are right in saying that there are D plus 1 parameters, but I asked about the coefficients. So interviewer will not accept that. Just letting you know. Okay, so we have a total of these D plus 1 parameters. Okay, so we are minimizing this function, which is yi minus yi hat whole square with respect to these d plus 1 parameters. Okay, and this yi hat is this theta naught plus theta 1 x1 I and so on till theta dx di. Okay, this is what we are minimizing. You can put a 1/2 outside just for some clarity's sake. Okay, it will not affect the thetas. Okay, it will not affect the thetas. So in every iteration, okay, in every iteration, can you tell me how many weight updates will I do? In every iteration of gradient descent, how many weight updates will I be doing? I will have to update every parameter, right? Just like I showed you, if you were doing univariate regression, simple linear regression, we started with this example that we had, if one feature we had, okay, you only had one feature. How many total parameters were there? 2, right? M and C. So you are updating 2 parameters in one iteration. So this time you have how many? D plus 1. So you'll be updating D plus 1. So I'm going to write it just generically. So look at this. I'm going to update every theta. So J starts from what? 0, 1, 2 up to D. So I'll be updating theta 0, theta 1, theta 2 up to theta D. So put initial values of theta 0, theta 1, theta 2 up to theta D. Some value you take. You can initialize all of them by 0. You can initialize all of them by 1. Any number that comes to your mind. Put it randomly. Negative, positive, whatever. Okay. You are in iteration m plus 1. You are updating it with respect to the previous value and then eta multiplied by this function, which is j. You are taking the gradient with respect to theta j at the value of theta j m. Okay. Is this clear? It's the same equation that I wrote earlier. Okay. Is this clear? It's the same equation, right? I haven't changed anything essentially. This is the same equation. It's just that I have more parameters now. Nothing special.
Yes.
Previously I had 2, now I have d plus 1. Okay. I want you to focus on this, the gradient. Okay. So I'll show you what this gradient is. Okay. So this is my function. I have to compute this gradient. Okay. With respect to some theta j. J can be anything, 0, 1, 2 up to d. So one change that I'm going to do, I'm going to write it like this. Okay. I'm going to write this. So this is theta naught plus theta 1 x1 I up to say theta d x di, right? Can I write it like this? Theta naught of x naught of I, where x naught of I is always 1.
Yes.
I can write it like this, right? Where x naught of I is always 1. So do you remember when I showed you the normal equations for which the solution was x transpose x whole inverse x transpose y, what did I add in x? So if these are my features, I added something in this x. What was it? Does anyone remember? I added one special thing to this to make it x. If you were there in that class, I believe it was the last class only. I added one more column to this. I called it as x naught. And what was x naught? It was always
1.
1. Do you realize that why it was added now? This should give you the idea. X naught I. Okay. So the idea is, okay, this particular column x naught gives me theta naught. This particular column x1 gives me theta 1. This particular column gives me theta 2 and so on. Okay, so I just made the equation a little generic. That's why you write it like theta naught x naught I, where x naught I is always 1. Okay, so it's the intercept term for a feature which is always 1. Okay, so just for reference sake, okay, why do you add theta naught x naught I there? So this is easier to remember it like this. Okay. Now I'm going to differentiate this function. My j, as you will see, is this yi minus yi hat whole square 1/2 of this. You are trying to minimize this function, okay, with respect to all your thetas. I'm going to differentiate this. Please try to follow it. This will be a little intricate, okay, but if you remember the rules of differentiation, you'll be able to follow it. Okay, you tell me for which theta I should differentiate. Theta 0, theta 1, theta 2, for which theta I should differentiate?
Let's take the first one, theta 0.
Theta naught. Okay, let's try for theta naught. Okay, so this is my equation that I want to differentiate. What is yi hat? Theta naught x naught I plus theta 1 x1 I and so on till theta d x di. Okay, please note that we are doing partial differentiation because we have multiple parameters. If you have multiple parameters, you cannot do regular differentiation. Okay, and there is a half here. I forgot that half. Okay, all right, how to differentiate this? So half is a constant, so half will come out. This power 2 is going to come out, and this will be I equals to 1 to n yi minus yi hat, and the power would now become 2 minus 1, 1 power reduced, and then you will differentiate this yi minus yi hat with respect to theta naught. Any questions up to this point? Any questions up to this point? Okay, again, if this is not clear, let me just rewrite this again. How do you differentiate a to the power of x of n with respect to x? A is a constant.
Take the constant out.
Take the constant out, and then you write x to the power of n minus 1,
Minus
and
1.
then you write dx by dx, right?
And a into n also.
Yeah, my bad. Yeah, n will also be there. Okay, thank you. Yeah, sorry. N will also be there. The power n comes out, and this is what you do, right? Yes or no? So the power n comes out. A is a constant, it was taken out. So what is x here? X is this. X is this. Okay, is this clear? See the relationship and perhaps you'll be able to follow. Convinced?
Yes.
Okay.
Yep.
All right. So subtract, cancel out this 2. That's the reason I kept this 1 by 2, to make it simple. Okay. It was just for mathematical simplicity. It will not change anything. Even if you keep this 2, it will not change anything. Okay. Summation I equals to 1 to n yi minus yi hat. Okay. Derivative of yi with respect to derivative of theta naught minus derivative of yi hat with respect to theta naught. What would be this term? It's the actual value, and you are differentiating it with respect to a parameter. So what would be this term? It's a constant. Yi is a constant. It's a given value for output, 0. Only this term will be valid because yi is the prediction. Okay. And what is yi? Focus on this term. Okay. This is your yi. Okay. Yi hat. Let's put this.
Certain,
Yes.
like how the thing was getting cancelled. I don't.
The differentiation of a constant is equal to what?
Okay. That. No,
Okay.
now I get it. Yeah.
All right. So summation of I equals to 1 to n yi minus yi hat, okay, into this minus of d of yi hat theta j or theta 0. This minus, I'm going to take it inside, so I'll make it like this. Okay. All right. Let's see what is yi hat. Okay. So this will be theta naught x naught I plus theta 1 x1 I and so on till theta d x di. Okay. So I'm going to write this term. Please see to this carefully. So I'm going to differentiate theta naught x naught I with respect to theta naught. I'm going to differentiate theta 1 x1 I with respect to theta naught and so on till theta dx di with respect to theta naught. Now, if I'm doing it with respect to theta naught, what would be theta d? If I'm going to do it with respect to theta naught, what would be theta d treated as? A constant.
Sure.
And what is xdi? It's the ith sample value of the dth feature, right? It's again a constant. This will be 0. All the values will be 0 except for this. So what will this give you? X naught I is what? It's a constant, take it out. You can write it like this. So what is theta naught by theta naught?
One.
So x1, sorry, the xi was like an input. So because of that, it's a constant.
It's a
So
constant.
if we were differentiating the constant, then it will become 0, right?
0 and up, because we are differentiating it with respect to theta naught. Every other parameter will be a constant, right? It's partial differentiation.
Okay.
So theta 1 into x1i, theta 2 into x2i, they are all constants. Okay, so that's why they all got eliminated. They are all zeros. Okay, they are all zeros. Okay, only the first term is non-zero, which is actually what? X naught I.
X naught I, yeah.
Okay, so what you are left with is this.
Summation of n.
Please note that I've changed the signs, okay, because there was a minus sign associated previously. Okay, and this is x naught I. Okay, this is the differential with respect to theta naught. What do you think the differential will be if I do it with respect to theta 1?
We'll just change the last one.
I-
Like
Last, it will change
yeah.
to x1i here, right?
X1i, yeah.
Okay, if I do it with respect to x2, what will change? X2i.
X2i.
Okay, so if I write it generically, let's say if I write it with respect to some theta j, what is this? Summation I equal to 1 to n yi minus yi hat. Sorry, it's actually the reverse, yi hat minus yi into xji. Does this make sense? Yes, people. Because you do it for any j. J is 0, 1, 2, up to d. It's just that the last term changes. It becomes x naught I, x1i, x2i, and so on. Okay, depending on what theta you're differentiating it with. Is this clear?
Yeah.
Okay, now let's focus on the weight update. So what was the weight update? Theta j of m plus 1 is equal to theta j of m minus eta times this gradient. Okay. Okay. Where you can say where x naught I is always 1. Because there is a special exception, right? We are adding this x naught column, which is not there, which is always 1. So that's why I've highlighted it. This is the final weight update equation that you have. Okay. So you're going to repeat this process. Okay. So repeat this process for every iteration. Okay. Repeat this process for every iteration. Okay. Till some convergence criteria is met. So convergence criterions were if the slope becomes very, very small or the difference in the error values become very, very small, less than the tolerance, or you can say that you're running it for fixed number of iterations. Okay. So those were the convergence criteria. These are actually called as the convergence criteria. Okay. How do you stop the process? Okay. These are called as convergence criteria. Okay. Now, you have fixed, okay, the weight update equations. So in every iteration, how many weight updates are there? J is from what to what? 0 to d. So d plus 1 weight updates are there. Okay. So for every weight update, what do you think is the most expensive operation? For every weight update, what do you think is the most expensive operation? Look at this equation, this should tell you.
A low, very low value of meter.
No, the most expensive operation I'm asking in terms of arithmetic. Summation part. Okay. What can you say about if you have a really large data set? Do you think it is practical? For every iteration, you'll be updating for d plus 1 parameters. And for every d plus 1 parameter update, you are going to take a summation of yi hat minus yi, multiplying it with xji. Yes or no? Does that make sense? This is going to be so expensive, right? Yes or no? It's not as simple, right? You have a very big data set, maybe 1 million examples. So every weight update is super expensive. Okay, super expensive. So there are strategies, there are researchers, what they have done is they have found out. So if the data set is very small, you do the summation on the entire set. Okay. You can do the summation on the entire set if the data set is small. There is no problem. Assume that the data set is big. Okay, this data set has a large number of examples. Okay, this one has a large number of examples. Okay. large number of examples. Okay. So you cannot accommodate this data set into memory. Okay? You cannot accommodate this data set into memory. In your computer RAM, you cannot keep the whole of it. That's what I mean by large data set. I mean, obviously you can keep it onto your hard disk, but I cannot accommodate it in my computer RAM. So what do you think I should do? If I cannot accommodate it in my computer RAM, do you think I'll be able to run this process?
No.
No, right? So that's not an easy thing to do. But what researchers have suggested is this. Why don't you break your data into smaller chunks? Let's call this first chunk as say batch 1. Let's call this chunk as batch 2. Just by looking at this picture, can you tell me how many samples are there in batch 1?
3.
3 samples. 3 samples.
Yeah.
1, 2, and 3. So you're going to run it for 3 samples. So the summation here runs for 3 samples. Okay. So this time, can you accommodate this batch instead of putting in the whole data? You can, right? It's just 3 samples. Okay. So let me ask you this. If you have say 10,000 samples, okay, and I break this data into say 10 batches, how many samples will be there in each batch?
1,000.
1,000. Okay. So you can decide on the number of batches depending on how much RAM you have. You would want to accommodate the biggest batch that you can. Okay. So generate the batches accordingly. Okay. Generate the batches accordingly depending on how much your RAM is there. Okay. And this is one concept that you will see frequently in deep learning because those data sets are exceptionally huge. They are multi-terabytes. Okay. When you actually start working on like industry level data sets, they are terabytes. Typically, when you download any image data set on your computer, it will certainly be more than 4 to 5 gigabytes if it's a reasonable data set. Okay. So we have to divide our data into batches, and this is called as batch gradient descent. Okay, this is called as batch gradient descent. So instead of running it on a whole, okay. So if let's say if all the samples can be accommodated, can I still call it batch gradient descent? Because it's just one batch.
Yeah.
Okay. All right. So when you are updating the thetas for okay. Yes, go on.
So it's not mandatory that I need to batching it. Like even if my data set is 1,000, like let's say that I'm only having 1,000, and I can put it in one batch. Like if that was not needed, like I have enough RAM storage, I can put it in one batch. Else I can split it.
Yeah, you consider all the samples in one batch. It is still considered to be batch gradient descent, but there is just one batch. Okay. But if the data set is really big, then you divide it into smaller chunks. I mean, that your RAM can accommodate, and then do this task. The same gradient weight update can be used. Okay. All right. So this is batch gradient descent. Now, what researchers realized, okay, instead of let me tell you one terminology first before I discuss the next type. So when you are updating, okay, when you are updating for a batch, that is called as an iteration. Okay. So per update, okay, you can call it per batch update is called as one iteration. Okay. All right. And when you go through the entire data set, this is called as an epoch. Okay. So per data set, it's called as an epoch. So in one epoch, can you tell me how many updates will be there? In one epoch, can you tell me how many updates will be there? Equal to how many?
Number of batches.
Number of batches. Okay. So number of updates will be equal to number of batches. And in every batch, how many weight updates will be there?
Number of samples in the batch.
Number of parameters.
Okay. Yes.
Okay. Samples are given in the batch, right? Okay. So per parameter update, you can say you'll be using number of samples. Does that make sense? Okay.
What is the epoch?
The epoch is just a name for it. Okay. So initially, initially when I said that, I'm going to run this process for every iteration, right?
Yeah.
So if the entire data can be accommodated in one batch, okay, epoch and iterations are the same thing.
Yeah.
Okay. But if you're now dividing your data into batches, so every weight update, okay, per batch, it's called as one iteration. Okay. So when you go through all the batches, okay, this will be called as one epoch. Assume that you had 3 batches. So when you have covered all the 3 batches, that is one epoch. Okay. So epoch and iterations, they mean different things, but if the number of batches are the same, then they are the same. Okay. So in one epoch, you have number of batches. I mean, those many weight updates. Per batch, you have D+1 parameter updates. Is that part clear? In this case, it's just a set of jargons that you have to remember. Nothing special. Okay. See, when you're doing ML on small data sets, let's say on Colab and all, these terminologies are the same, epoch and iteration. So nobody will say epochs. But when you move to deep learning, there you will see epochs. So don't get confused.
If I have a 10 batches, like even for the 10,000 data sets, like I let's assume like I'm having 10 batches, like, but still I have only one epoch because of if all batches can be
okay, let's look at this. You have say 10 batches, it will go up to batch 10, right?
Yeah.
How many samples are there in per batch? 1,000 samples?
Yes.
So take the first 1,000 samples, that is called as one iteration.
Yeah.
In one iteration, how many weight updates you did?
Number of
parameters.
Parameters, yeah.
Because all D+1 parameters will be updated. Okay. From this batch alone. Okay.
Yeah.
If I go to the next batch, how many parameter updates will I make again? Again D+1.
Again D+1, yeah.
So if you go through this entire batch, the whole time is called as one epoch. So in one epoch, how many total updates you did? Equal to the number of batches, right?
10 times. Okay.
10 times. Okay.
This terminologies were different, but the answers.
Yeah. So now do you understand like what is an epoch, what is
totally.
iteration? Okay. Got it. So this is batch gradient descent. Very, very simple. Okay. It's just that this is done to reduce the, you can say memory constraints. If you cannot accommodate your data set into your RAM. Now, the next thing is, why not? Okay, why not? See, I'm pretty sure no instructor will give you these many details. If you read any blog as well, you'll not get these details. Okay, they will just show you the gradient descent function without any arguments. But we are going to discuss all these arguments that I'm telling you right now. Okay, let's talk about. Okay, again, this batch gradient descent is will still take time, right? Yes or no? It's so expensive for bigger data sets. Now you are just running one epoch where all the samples are just, used. Why don't you think about this? Instead of taking all the samples from every batch, why don't I take a subset of the samples and do it? I'll just pick the samples at random. Don't you think that can be done?
Yes.
Yeah.
That is called as mini batch. Okay. So from every batch, you take a subset of the samples. Okay, to do your gradient descent. How many you do? Okay, see, I would want maybe say out of 1,000, maybe just 10. It has reduced my complexity 1 by 100 times. Okay, so it depends on you how much you can reduce. Okay, so you can still have bigger batches, but when you are accommodating into your RAM, you are just picking say 10 or 20 samples from that batch to update it. And let me tell you one thing. The randomization process that you have, right? It actually expedites your convergence, which might not be intuitive to you right now. I'll give you an analogy why the randomization actually leads to faster convergence. You will actually lead to a solution, the minimum, very, very quickly without using the entire data set. Okay. I'll talk about it with an analogy. We will do that soon. Okay. So mini batch selects a subset of the examples at random from every batch. Okay. Now another thing is there is one more variant of it, which is called as stochastic. This is called as stochastic gradient descent. And what stochastic is, it's like using one sample at a time. Okay. Using one sample at a time. Now, please note that I am not selecting one sample from a batch. I am just going through one sample at a time. So it is like my batch contains one sample. Okay, my batch contains one sample. Okay, is that part clear? So how many batches will be there, by the way?
Number of
In
samples.
stochastics,
10,000.
right?
10,000
Okay.
number of samples. Okay. Don't you think a gradient update can still work? What I've done is I've just removed this summation. I'm doing it sample by sample. Okay. This is stochastic. Let me tell you, if you use one, do you think that if I use just one sample to find the update, will it be good or will it be bad in general? What do you think?
With one update, we can't get a precise.
No. Just think.
The
Okay, will it be good or bad in general? Let's say you are
Bad.
you have 10,000 examples. It will be very bad.
Yeah, bad.
So the weight updates that you will see, they are very bad. But over a period of time, you will see that they have a declining pattern. They will lead to the minima, but they will fluctuate. So if you are thinking like this, let me talk about this. Let's say you are using, so this is your time, okay? Let's say this is your iteration number. For every iteration, we are running it, okay? You can call it epoch number as well, depends on how we are treating the batches or the whole data set. And on the y-axis, I have the value of j, the function, the error function that I have. Okay. By the way, this j is also called as the loss function. It's also called as the error function. It's also called as your optimization objective that you want to minimize. Okay. You can also call it minimization objective. Your goal is to minimize this, right? Okay. Now, my question is this. We are going to start initially with some set of thetas. What do you think the initial loss would be? Would it be very high or would it be very low? Initial loss. Think of, do you think you'll be so lucky that you will reach, I mean, when you guess the initial parameters, do you think you'll be lucky that you will always reach to the minimum with those initial guesses?
No.
No.
You will, right? Why? Why not? Why you will not reach? Think. I'm saying in steps, don't you think you will reach to the minimum? Why? Do you think, is there a possibility that if I start with some different initial values, will I not reach the minimum? Don't you think it is guaranteed that you will reach to the minimum? If I keep on doing, say, gradient descent for some number of iterations or epochs, why is it that you think we will not reach? We discussed about a property, about a specific type of a function which has only one type of global minimum. So if there is one type of global minimum, don't you think gradient descent will always converge? Assuming you have a decent learning rate. Yes or no? If the function is kind of the squared function, don't you think wherever you start, you will reach to the minimum? I start from here, I start from here. You will, right? That's why we chose the function to be convex. So all I'm saying is, wherever you start, okay, wherever you start, you will definitely reach to the minimum, okay? And let's say you're starting here. So your error value is very high, right? Initially. If I compute the j value at this point, it would be very high in comparison to the j value here. Yes or no? You can see the y-axis, right? This is j, by the way. Okay. The value which is above is higher. The value which is below, which is lower. We have to reach this value, which is the minimum. Okay. So after every update that we do, okay, if it was done using the entire data set, what can you say about the pattern of the curve? If I'm trying to draw this, I'm using the entire data set. What can you say about it? How will the loss look like? Will it increase or decrease with time?
Repeat your question, please.
The question is, I want to plot this curve, right?
Okay.
Iteration numbers versus error. I'm using the entire data set. Okay, I'm using the entire data set. I want to plot this. How would it look like? Will the error decrease with time or will the error increase with time? Will the loss increase with time? Will the loss decrease with time?
Error will increase.
Why would the error increase? You're thinking as if it will decrease. See, think about what J is. Don't you think we are measuring the error essentially? It's a square difference between actual and predicted values. You can put 1/2 also, that's also fine. Okay. It's error only I'm measuring, right? Okay. What will happen? This is a positive value. what will happen to the, to the error value in the next step? Will it increase or decrease? You want to reach to the minimum. It will decrease, right? Every step you are taking, don't you think you are going down?
Yeah.
So error decreases, right? And since this value is always positive, you will reach to a situation where you cannot minimize it any further. Because if you go to the right, you're actually having a more error value. I want to reach to this minimum value, right? And that is what you can determine with the help of gradients. Okay, the sign change in gradient. Okay. So how would this look like? Is it will be a decreasing function, right? Yes or no?
Yes.
If I plot this, don't you think this will be decreasing? So initially my error values are very high, and then it keeps on decreasing. And will it become zero? Do you think will it become zero?
Near to zero.
It depends on the data points. Do you think if the data is like this, if I give you one input feature, okay, if the data is like this, do you think the line is ever sufficient to pass through all the points?
No.
The only thing that you can get is the best line, which is probably like this. So is the difference between actual and predicted values ever zero? Are the distances zero?
No.
Of actual? So it will certainly be something, right? It will not go to zero. But after a while, you will not be able to minimize it. Okay, do you get that now? It is not guaranteed that this difference, actual and predicted, will be zero, right? Does it make sense?
Yeah, okay.
Okay, so this will not be zero. This is measuring the difference between, it's the sum of the distances, sum of the squares of the distances. Okay, this will not be zero, but it will not be minimized after a while. So if you start with this, okay, let's say this is iteration 1. What can you say about the sum of squares of the distances? Will it be high or low?
Initial, right? So
let's say we are starting with some initial MNC. So this line is, let's say M is 3, maybe say M is 3 and C is minus 2. Can I say this line is maybe say 3x1 plus 3x1 minus 2? Yes or no? This is the initial line.
Yeah.
Okay. If you look at this initial line, what can you say about the error? You can compute this error using this function.
Yeah.
You can compute this, right? yi minus 3x minus 3x1 minus 2 whole square. Okay. All right. Now put different values of the outputs and the corresponding inputs. Don't you think you can compute it?
Yes.
You can compute it for the entire data set. You will get an error value, J value for it. This will be very high, okay? Because you can see the points are very far away.
Yeah.
Okay. Now let's say I do the updates with the thetas. Maybe this line will move something like this. Okay. Now do you realize this line has become better? It has become closer to the points. So after every update, you will see that this line is moving closer and closer and it settles. It doesn't change after that because there is no change in MNC, no significant change in MNC because the slope is now very, very close to zero. Okay, that's what this means. So all I'm saying is that if you look at this iteration 1, iteration 2, iteration 3, 4, and so on. So with iteration numbers, this is going to settle after a while. Okay, and it will not go to zero. Okay, this is when you are using the entire data set. This is also called as full gradient descent, by the way, when all the samples can be considered into one batch.
If that was not reaching to minimum, like where it will range from, like as we said, like the minimum will range between 0 to 1, right? So where this...
No, when did I say minimum will range between 0 to 1? It depends on the data, right?
Okay.
See, do I know the minimum of this function without plotting it?
No.
So how can I tell you what is the minimum? I just showed you for a function 3x squared plus 6 because I knew the minimum for it.
Okay.
I want to find the values which lead me to the minimum. Okay.
Okay.
All right. So this is full gradient descent where you are using all the samples in one batch. If you divide the data into smaller batches, okay, where batches are now containing a subset of the examples, what you will observe is that this will kind of fluctuate. Okay. But the fluctuation will be very, very little because there are a lot of samples in every batch. Okay. It might go up, it might go down, but after a while, this is kind of settled. Okay. There will still be fluctuations, but the pattern will be decreasing. This is the curve for your batch gradient descent. Yeah, this is the curve for your batch gradient descent. Okay. What do you think will be the curve for your mini batch gradient descent? Will there be more fluctuations or less?
Less fluctuation.
Even more. You are using only a subset of the examples of in a batch. You're not using all of them. So it will be like this. It will be like this. But the pattern would still be decreasing. The pattern would still be decreasing. The fluctuation would be more. And what do you think about stochastic? You're using now one sample.
That will be stable.
Even more
More,
unstable.
right?
Even more unstable. It will be even more unstable, like this. Okay. But the pattern overall will be decreasing. Okay. And what you will feel is that, I mean, what you will observe is that stochastic actually will converge the quickest. Okay. Stochastic will actually converge the quickest. Okay. If you try to see the weight updates, let's say after say some 7 epochs or 8 epochs, stochastic, because of the randomized nature of picking of the samples, okay, it will actually lead much closer to the best fit line. Okay. All right. So let me just give you an example why this happens. Okay. Let's say this is the data set. So this is the data set. I want to start with some initial sample. Okay. Maybe say I'm going to start with, probably let me remove some of them. Okay. Maybe say I want to start with this example. So I'm starting with some initial values of MNC. Maybe say this is the initial line. Okay. This is the initial line. All right. So I have some MNC values, which gives me this initial line. Now I'm going to use one sample. So if I use this one sample alone, do you realize that this sample is going to push this line significantly upwards? Yes or no?
Yeah.
You're not using essentially all the points, you're just using, maybe you get to this. Okay, you get to this because of that one point. Let's say you use this as the next step. You'll come back like this. Do you realize that because of the randomized nature of picking of the points, the kind of, so if this is the best fit line, let's say if this is the best fit line, maybe say this is your best fit line. Can I say that because of the randomized nature, see, it is not guaranteed, but can I say that it is more likely that stochastic gradient descent will lead me to this solution much quicker than batch and full? Yes or no? See, okay, think about how much time one iteration update will take for full gradient descent. Will it be, okay, I'm talking about one iteration update. In one iteration update of full gradient descent, how many samples do you use? All of them. So you're going to do a significant number of computations in it, okay? And you're going to utilize all the samples. And basically it is going to push depending on all the samples, okay? Here you are focusing on one sample, okay? So it will be how many computations? Just for one sample.
One.
You're not going to compute it. So the time taken is actually significantly lesser. Okay, it is 1 by n if n number of samples are there. And further think, if I use just one sample, obviously the fluctuations you see are very significant. The lines will change significantly after every step. But what I'm saying is, after a while, when the fluctuations are kind of settled, they will lead much. So it may be like this. More iterations are required by stochastic gradient descent to reach a solution which is closer to the best solution. But every iteration does not take much time. In full gradient descent, maybe you require more iterations, less iterations, but every iteration takes a significant amount of time. Do you realize the difference?
In my better understanding, I'm saying like the stochastic will be fit for a smaller data sets.
Bigger data sets. If you have small data sets, you will kind of fluctuate. You will never settle. Okay, this will just go up and down. I mean, it will be just all over the place.
Yeah, but as you said, like, you know, if you have a more like the bigger
see, if you have more
sets,
examples, okay, you can think of it like this. If you have more examples, perhaps the chance that I select a good example from a bigger data set is much better than the chance that I select from a small data set.
But if my data set has let's assume like having a 10,000 samples or 10,000, like my data set has a 10,000
Mhm.
data. So at that time, if stochastic has to run, like it will take each and every samples, right?
Stochastic will run, yeah, it will take each and every example, but the
So-
examples will be chosen at random. I mean, when I say chosen at random, you can think of it like this. I mean, every example is chosen, but it is chosen like this. So I give you a data set, right? I give you a data set.
Mhm.
Are you thinking that the ordering is like this? This is first sample, this is second sample, this is the third sample.
No,
Are you thinking like this? No, right?
no.
It
Like
can be the second sample might be this, right? Third
Yeah.
sample might be this. So I'm saying because of the randomized nature of the orientation of the samples, the line will actually settle much quickly. Even though it takes you more number of, I mean, you can put it like this, okay? See, in stochastic gradient descent, how many weight updates do you do? Think about it first. Okay, let's talk about one whole data set, okay?
Okay.
In one whole data set, how many weight updates will be there? N samples multiplied by D plus 1. For every parameter you'll be updating. Let's say you are updating only one parameter. Can I say these many weight updates will be there? Yes or no? Because you are taking one sample at a time.
Mhm.
Does that make sense? Okay. So how many iterations did I run? I ran n iterations. Is that part clear?
Yeah.
Okay. I am saying let's look at full gradient descent now. Okay, I'm looking at full gradient descent now. How many weight updates do I do in one whole data set? Okay. Look at the full data set. How many weight updates do I do? Only D plus 1. So
Yes.
if you have one parameter, you will do just one update. But doing this one update is going to take how much time? It will use all the samples. Okay.
Yeah.
Do you think you require all the samples, okay, to do a good update, or you require these n samples one after the other to do a good update? Which is better? The way you select these examples one by one can actually lead to a much quicker convergence than using all of them in one step. Okay, or rather, let me just show you a visualization. Let's see this. Okay, 1 second. Okay, let me show a visualization. Perhaps this would be clear. I believe you are not able to catch the idea of how randomization will help. I can understand this is not intuitive to, I mean, in the first case, but let's look at this.
Yeah, if it is random, like it will take the first value and then the 200th value and then the 700th value. That is fine, but I'm little bit
Just a
lacking
second. Okay.
somewhere. Yeah.
Okay, that's okay. 1 second. 1 second. Okay. Imagine that. Okay. Only focus on the figure on the right. Okay. This is the initial value. Okay. This is the initial value of some MNC that I chose. So this line is some M times X1 plus C. Is that part clear?
Yeah.
Okay. This is the data set that I have. Initially, I chose some initial value of MNC, and this is what I get. All right. If I use all the samples, where do you think the update is going to take me? Assume eta is 0.1. Do you think it will reach like this in the first iteration itself?
No.
No, it will be just slightly moving like this.
Yeah.
Okay. All right. Now I want you to focus on what will happen if you're doing stochastic. Let's say, okay, out of all these samples, whichever sample that I pick, out of all, let's say if it was picked from any of these samples which are above than this, if I pick any of these samples, don't you think this line will move much more quickly towards, you can say, towards the best fit line? If this is the best fit line, let's call this to be the best fit line. Let's say this black line is the best fit line. Okay.
Mm-hmm.
Which will move quicker? The stochastic one, if you there you are using just one sample right now.
Yeah.
Or what do you think if you take all of them, which will move quicker?
For sure stochastic, because that is taking the random so that we
And
get
how much time does stochastic take? One sample only.
One sample.
Okay, so it's, see, I'm saying that the movement of this stochastic, it's going to be super quicker in comparison to using this like best fit from, in comparison to doing a weight update on all the samples. Okay, so I'll just show you in the next iteration, it will probably become like this if you are using full gradient descent. But if you chose, say, this point and you were doing stochastic, you would probably move like this in first step itself with just one sample. Okay, with just one sample. Let me show you if you were doing full gradient descent. Okay, you would probably move like this. Okay. And if you would have chosen maybe say this sample, you would probably settle like this. Okay. All right. And you're just using one sample. Okay. It just depends on where that sample is chosen. Okay.
Okay.
So if you have more examples, don't you think you are more likely to settle quickly because of the randomization of the samples that are chosen?
Sure.
Okay. Now do you get it? If I have less samples, you can say that maybe one time it goes like this, maybe one time it goes like this, maybe one time it goes like this, maybe one time it goes like this. It kind of unsettles. Okay. Stochastic is not good for smaller data sets. Okay.
Okay.
So you need to have a significant number of samples in the hope that the next sample that is chosen, okay, is a good sample. All right. Most of the time it will be a good sample if you have a bigger data set.
Okay, so in some point of time we'll know that okay, this line is fitting, so that we'll stop it at the time. Instead of this was taking a more time, and each like moving towards the resolution was very slow. Now I totally get it. Yeah.
Okay, so let me talk about maybe how to stop stochastic. Okay, what stochastic says is this: if when you're picking these samples, and let's say in 5 successive iterations, the error has not changed much, the line has not deviated much, then you can stop.
Within 5?
Within 5 steps, because now you're doing one sample at a time, right? Okay. So if in the next 5 steps, okay, that you chose, the line is not deviating much, which means you are very, very close to your good solution. Okay.
Oh, that's much fast. Okay.
Okay, so that's why I'm saying the randomization process of stochastic is likely to be the best. Okay, and when you see the implementation of gradient descent, it will always be with stochastic.
Okay,
it will not
5
be with...
steps means like will be.
No, I'm not saying it will be done in 5 steps. I'm just saying the convergence criteria for stochastic gradient descent is, so you run this process for one sample at a time, right? I am saying that where to stop this stochastic, because it will keep on fluctuating, right? So I am saying that when you are looking at 5 successive iterations, 5 consecutive iterations, if the difference between the errors in these 5 successive iterations is not much. Okay, the line has not changed much, even after you did 5 random updates, then the line has probably settled. Okay. That is where stochastic stops. So stochastic is unlike your normal gradient descent, which typically stops when the difference between 2 adjacent iterations, 2 consecutive iterations is less than the tolerance. Here you look at 5 iterations, not just 1. Okay, you can increase the number if you want. Okay, you can increase this number if you want. Okay, so this is the idea behind stochastic. It typically works very, very well, and you will only see the implementation of stochastic in your sklearn library. You will not see any other. So are the different techniques clear to you, to everyone, that we discussed how to solve? That will be used to solve for linear regression. So we started with your derivatives, okay? And we found the solution for univariate case. We derived for, I think, C, and I asked you to go back and do it for M. So you found that C was y bar minus M times x1 bar, and your M was covariance of x1 and y divided by variance of x1. Okay, this was the univariate solution that we tried, that we saw in the very first time. Then I showed you that for multivariate, you can go by differentiating all the functions, okay, with respect to your thetas. Okay, you'll get d+1 equations, d+1 variables equated to 0, solve it using substitution or elimination. Okay, but this was not preferred, so I talked about a solution which was the closed form solution. also called as normal equations, also called as analytical solution. This was all thetas are x transpose x whole inverse x transpose y. See, please note that all these solutions are the same. All these solutions that I've showed you, they are the same. They will lead to the same result. We will see that in the implementation. And then we spoke about gradient descent. And we saw different versions of gradient descent today. So starting from your full gradient descent, let's say after that we saw batch, we saw mini batch, and then we saw stochastic. So stochastic is the one which you will see in the implementation. It uses just one sample. Okay, that's how it doesn't have to keep the entire data set into memory. All right. So any questions about gradient descent in general or linear regression in general? Yes, people. Any questions about it? See, please ask. I would appreciate if you ask me now instead of writing to the GUI team later on. I couldn't understand anything. And if you don't ask me anything, then how would I know? You are not in front of me. I can't see your face. Okay, so it is like saying this. Okay, I mean, I don't understand anything. Do something about it. Okay, and you do not even care to do something about it. So please ask if you are not understanding anything. Or if you have understood something and it is not clear, still ask. Because many of you did this last night. Or maybe a couple of you did. I don't know the numbers, how many did. But yesterday's class, I believe, went over some people's head. And they didn't even ask a single question. And for those of you who did, and yes, you still feel as if I'm going too fast, tell me I'll slow down. You just have to say a word. Okay, so speak or write. Okay, I will not take your name. Okay, speak or write. Okay, that's how I'll know if I'm going too fast or too slow. Okay, so any questions?
No, Santan.
Okay, from anyone else?
No question.
Okay, thank you, Shilpa. Anyone else? So I'll presume if you're not answering, you don't have any questions. Okay, because that's the only thing I can imagine, right? I can't see you. If I were in front of you, I would have seen your face and I could have probably tell, okay, if you need more help or not. But since your videos are not on, I can't tell. Okay. So be courteous and be thoughtful when you write something. Okay. See, I'll be very frank. If you think you require a change in mentor, do reach out to your GUI team. They will change me to someone else. Okay. And I'm happy with that. Okay. Because I don't have any, what we say is, I mean, I have sufficient batches to take. Okay. They'll give me another batch. So if you're thinking that you will do something wrong by me, don't worry about it. If you feel that, okay, it is becoming difficult for you, you can request for a change in mentor. Okay. Because see, you have paid, so you should learn. But if you are not asking and you do this, then you are the culprit. Okay. I'm not. I'll be very straightforward with this. Okay. So since you have paid, I want you to learn. That's why I keep on asking, ask as many questions as you want. Okay. So I don't mind answering any number of questions. Okay. But during the session only, not after the session. Okay. All right. Okay. So we have seen different variants of gradient descent. Now I'm going to show you how to do, and we'll do all of this in the implementation. I want to cover all the details first before we before we see the implementation of all of it, because all the implementation can be done in a limited time. This is what is needed for you right now. Let's try to discuss how to fit. Yes, go on. Any questions? Yes, people, any questions? Okay, I don't see any chat here. You can write to mentor if you're writing, okay? All right, let's see the next idea, which is how to fit polynomial functions, okay? Imagine my data is like this. See, please note that I'm using one feature right now. You can use any number of features, okay? If my data is like this, what can you say about which feature is, okay, Divya says I'm facing difficulty in understanding maths topics. How do you overcome that? one thing I suggest you is first read about differentiation. Okay, once you have read about differentiation, then read about gradient descent. Okay, try to read it on your own. And once you read about gradient descent, and if it is still not clear, rewatch these two lectures today and yesterday's and today's. Okay, and if it is still not clear, use anyone else. Use anyone else as a resource, and then we can discuss it tomorrow. But you need to spend time. If you think that you can get everything in this session, probably it's not the same for everyone, right? Everyone isn't the same. So if you're facing difficulty, please know that, okay, invest more time, okay? Invest more time. And I'm here to help, okay? You should ask questions. You're saying this for the first time. So you should ask me any number of questions, okay? If you're struggling, just ask me, sir, why is this, or how is this happening? Or what is this, okay? I'll be happy to answer, okay? But you need to ask, okay? So if you don't get anything, just ask, all right? So maybe look at this topic and tell, you can interrupt me any number of times in between. I don't mind that. Okay.
Sure, Santanu. Okay,
let's see this. We have just one feature right now. See, with one feature, I can actually draw this curve in 2 dimensions. You can see I have plotted the data in 2 dimensions. So I have this data set as x1 as y. You can say that I'm trying to determine maybe say height from h. Okay. So this is how the data looks like. Do you think a linear function is sufficient to do this? Do you think a line is sufficient to fit to such type of data points?
No.
Probably no, right? It doesn't look like it, right? The best that you can do is probably something like this. Yes or no?
Yeah.
But all these points, what about the error on all these points? It will be very, very high, right? The distances with respect to the best fit line would be very high. So regardless of wherever you fit this line, okay, maybe you can think of, maybe I'll go like this, okay. This line is still not sufficient, okay. But do you know of any such function which is a good fit for it? What shape are the data points resembling? Maybe say these are some more points. Like which shape is this? It's called as a certain shape in mathematics.
Okay.
Parabola. And parabola equations are of what degree? Quadratic equations. Okay. So we are going to now see quadratic equations. Okay. So if you have an idea about how the data set looks like, okay, you started with linear, so do linear regression. Okay. Now I'm going to show you how to do quadratic. Okay. If you cannot even visualize the data, you try linear, quadratic, cubic, and so on. And whichever gives you the best results, you go with that. And that is what I'll show you how it is done. So let's try to see how it is done for quadratic. Okay. Just a second, please. I need to take this. Okay. Just give me a moment, please. Sorry, guys, there was a delivery person. So see, here I can visualize the data, so I can fit any type of function to it. Okay. It seems reasonable if I fit a quadratic function to it, which would be probably of this shape. Okay. So how do I fit the best function that I can? See, maybe this quadratic function would be like this, right? Is this a good function here? No, right? So maybe I have to find the best quadratic function like this. Okay. How do I find that? That is the question. Yes.
This may sound silly, but like a curve, a convex, and then the quadratic, everything like looks same while we were drawing, right? Like Maybe.
See, the error function, okay,
Okay.
is quadratic. Okay, so quadratic functions look like how? A parabola.
Yeah.
We are now doing regression using a quadratic function. It will be also a parabola. Yes or no? It will be a parabola, right? Quadratic functions are parabolic.
Okay. Okay.
Okay, they are convex. Okay, they are convex.
So
Quadratic functions, yes.
are all these three are same, or like, because
No,
like
they are
when I'm-
different, right? See, forget about, see, you are trying to relate multiple different concepts. Error function, if you remember, what was the error function? It was sum of squared errors, right? It's a
Yeah.
squared errors. It's a
Yes.
quadratic function. Okay. A quadratic function looks like a parabola. Okay.
Okay.
Here we are trying to find one function which is again a quadratic function but fits best to your data points. Okay.
Okay.
All right. So we will use the same quadratic loss function. Okay. But this time, so from the quadratic loss function, what do I determine? Previously, when I did linear regression, when I minimized the quadratic function, what did I get? The MNC.
The MNC, yeah.
But MNC are what? They are giving me a linear function, right? This time I'm going to use the same quadratic loss function, but they will now give me a quadratic function. They will give me some parameters that I will substitute in a quadratic equation, and you will see the function will come like this. This is not the loss I'm drawing. This is the best fit. See, how do I draw the best fit line? I draw the best fit line probably if this was the data set. I would draw probably like this, right?
Yes.
Yes or no? But this time I'm going to learn a function which is like this.
Okay.
It's not a line anymore. It's a function. If you want a cubic function, it will probably be like this. Okay.
Okay.
So I'll show you how to fit different functions. See, again, revise. If you're thinking that you'll get everything in the class, probably not. I understand maths is difficult. Okay. And we have limited time. Okay. I understand that. Okay.
Yeah.
So this time what we are going to do, we are going to use the same quadratic loss function that we had. This one. Okay. I didn't want to discuss this right now, but
No.
yeah, still going,
Actually, I didn't ask about this kind of thing. Like I was Googling the images like convex, parabola, and everything. Like everything looks like same to me. So that's
okay, no, you can make functions that are, not parabolic and they are still convex. This is also a convex function. Okay, does it resemble a parabola? No, right?
Yeah.
But you can say, okay, maybe it resembles a parabola because it's like a V shape.
Mm-hmm.
Maybe I'll show you a function like this. Okay, maybe a three-dimensional function. Can you make a bowl? Okay, like this. Is it a convex function? Think about a piece of paper folded like this.
Yeah.
It resembles a parabola, right? If the function is convex, don't you think it will be a parabola? Even in high dimensions, because parabolas are something that are going to the top. So if you have to come down, it has to be looking like a parabola, right? So all shapes that have a global minimum, they will resemble some kind of a parabolic structure, right? They'll be very, very close to parabola. Okay. All right. Because you have to find the global minimum, right?
Sure. Like I was simply Googling convex image, parabolic
No,
image.
they will all give you simple examples, right? In 2 dimensions, 3 dimensions, and so on. So please note that functions can be convex, but they will have a similar shape to a parabola because you have to come down. Okay. But the way these functions are defined, they might not be differentiable.
Okay.
We are using a specific kind which is differentiable and actually resembles a parabola. Okay. All right, let's see this. Okay, let's see this. So, okay, so I want to fit a quadratic function to this. What is the equation of what is the quadratic equation? Like, how do you write it generically?
X plus bx plus c.
Bx plus c, right? Okay. And so in mathematics, I find what? The roots, right? Yes or no? I find the roots. And the roots are what? X, right? I know A, B, and C, by the way.
Yes.
Do you remember the formula minus B plus minus the discriminant and square root of discriminant by 4AC? Right? So you find the roots of it. In my case, if I want to fit a quadratic function, do you think I can write it like this? Theta naught plus theta 1. So if it was a linear function, how did I write it? I write it like this, right? Mx1 plus c. Yes or no?
Mm.
It's just bx plus c. You can think about it. This is just bx plus c, where b is m and c is c. Okay. Now I wrote it like this: theta naught plus theta 1 x1. Okay. So I'm just writing it like this. So this was a linear function, right? Now I'm going to write a quadratic function. And what is the unknown in this equation? Is it x or is it theta?
Theta.
Theta.
Theta. So in my case, I am going to determine these coefficients, thetas. Okay. I'm going to determine these coefficients, theta naught and theta 1, the parameters. Okay. So if I'm going to write a quadratic equation, how would the quadratic equation look like? Theta naught plus theta 1 x1 plus theta 2 into x1 squared. Yes or no? A is simply this theta 2. Can you relate to this? And the feature value is what I have squared. Okay. Now the beauty is this. If I give you this data set, which is x1 and y, don't you think that whatever this value is, I can just square this value and I can get x1 squared? Yes or no? Don't you think if I have b1, I will just square this b1 square? So why don't you treat this x1 squared as another feature, let's say x2? This is a column, right, that you just generated from the original column. I can call it as x2 also.
Yes.
Okay. Does that make sense? I just created a new feature from original feature. And now I can still use linear regression for it. See, because if I write it like this, theta naught plus theta 1 x1 plus theta 2 x2, is it linear? First of all, tell me this. Is it linear?
Yes, this is linear.
In terms of what? In terms of?
Power of x.
No. Sorry, guys. Okay. So the idea is very simple. Okay. I was asking this question. Okay. Let's even consider this equation. Would you call this equation as linear?
This one is not.
Okay. This one is linear in terms of what?
This one is linear in terms of x1 and x2. But in terms of x1, it is quadratic.
Okay. But what is it that you are trying to determine? Are you trying to determine x1 or x2?
No.
Think. What are you trying to determine? Are you
Theta.
trying to determine the thetas? So is this equation still linear in terms of your thetas?
Yes.
So don't you think I can still use linear regression?
Yes.
But look at this equation. What is it that you're determining here? Is it A, B, C or X?
X.
X. So you call it as quadratic, right? Why do you call it as quadratic? Because X has the highest power as 2. In this case, when I'm determining the thetas, do thetas have any power as 2?
No.
So can I say it is still linear in terms of my thetas?
Yes.
Both the equations are still linear in terms of my thetas. Okay. It's just that I will treat x1 squared as another feature. And this is actually called as a quadratic feature. So in general, do you think that I can put any power to the original x1? Yes or no?
But then if I'll increase the power of x's,
I'll just need one more theta to learn.
no, that is fine. Like theta is fine. I'm increasing my parameters. But my ranges of the features will also increase.
Yes, definitely they will. They will. You'll normalize it. You'll normalize it. Okay. You'll normalize it, right? I don't deny that. Okay. I don't deny that. Okay. Do you think they will actually matter? Let's say you have squished it between 0 to 1. If you square it up, will any value go beyond 0?
No.
Will any value go beyond 1?
Mm.
No. Why would it go beyond 1? Even if you square anything which is between 0 to 1, it will actually become smaller. Yes or no?
Yes.
Think about cubic, think about power 4. It will still be between 0 to 1. So do you
When
think is there a need to normalize?
No, when I do it for 0 to 1 range, then there's no need.
That is what, okay, that is what you will do. Okay, that is what you will do. Okay. So can I say that my equation is still linear in terms of my thetas and I can still do linear regression, but I will just need to create more and more features. So let's say I'm doing cubic regression. How many new features will I create if I give you this data set? I want to do cubic regression. 2 more, right? What will be those features? X1 squared and X1 cubed. This is as simple as this. So your prediction function would be like this: theta naught plus theta 1 x1 plus theta 2 x1 squared plus theta 3 x1 cube. If you are not comfortable with squares and cubes, you can write this as x2 and you can write this as x3 because it is just another column that you created. Okay, so this is like x2 and this is like x3. Okay. If powers bother you, this is it. You can still use linear regression. Just create this data set and apply linear regression to it. So you can use stochastic gradient descent on it. You can use the closed form solution on it. Okay, both can be used. Does that make sense? As simple as that. Is this clear? Yes or no? I just have to determine the thetas, right? Thetas I will get from linear regression. So I'm still minimizing this function, yi minus yi hat whole square. This is that yi hat will become this. Okay, if you are trying to do cubic regression, let's write I at the as a subscript. Okay, does that make sense? Can you say yes or no if it's clear or not?
Yeah, so in any case, we can use linear only then.
Yeah, you can use linear. You just have to create more features. Okay, and pass it to your linear regression input.
Okay.
So everything will stay the same. Nothing changes. That's why I said polynomial regression is actually simpler than linear. So if you understood the concepts of linear regression, just create more features and apply linear regression to it, and you are done. Okay, we will see how the functions look like. We will plot it and we will see, okay, this is what you will get. Okay, so this is the concept of polynomial. I need to discuss one more concept, and this is the most important concept in ML. It applies to all machine learning algorithms. This concept is called as regularization. Okay, let me describe what this concept says. Okay, so before I describe this concept, I want to discuss something. So if I give you a data set, okay, if I give you a data set, I typically split it into 2 parts, train and test. So on the train set, okay, I make my model. So let's say I will get the thetas from my linear regression, and then I will test on the test set what is the performance using some evaluation metric like mean squared error, sum of squared errors, R2 score. You can use any of those metrics. Okay, you know whether they are higher the better or lower the better. You know about those things. So if I'm going to compare maybe say 2 different linear regression models, one with say degree 1 and one with say degree 2. Let's say I'm measuring mean squared error, and this is for degree 1 and mean squared error for degree 2. I'm measuring it on the test set. Okay, I'm measuring it on the test set. Let's say this one comes out to be 100 and this one comes out to be 200. Can you tell me which degree is better, degree 1 or degree 2?
1.
Degree 1, right? Because lower the better. Okay,
Yeah.
I hope this is clear. All right. Okay, now we are going to discuss a little bit in more detail. See, every machine learning model suffers from a problem, and the problem is this. See, every learning, you can say algorithm, or even if you think about humans, okay, humans have a problem of cramming. Once they see things, okay, they try to cram it. I'm not talking about like humans which are adults, because they can generalize also. Let's talk about babies. Okay, so if you show babies, let's say 3 colors, let's say green, blue, and red, and if you show the baby a different color, do you think the baby will be able to recognize? the fourth color? Wouldn't the baby say it is one of the three colors which the baby has seen before?
Yes.
Okay. Because as humans, I mean, when we grow, from our experiences, we generalize, right? But if you show a baby which is like in a nascent stage, it has just, I mean, it was just born. Let's say you are teaching the baby to, describe some colors. The baby will just respond, okay, this is one of the three colors because it has seen only three colors so far. Machine learning models have also the same problem. The problem is that they overcram the samples that you show them. And this phenomenon is called as overfitting. Okay, I will just describe the problem. Let's say this is the data set. Okay, this is a small data set. Maybe I'll make it like this. And this is the train set. Okay, so once somebody gives me this data set, okay, I have these points x1 and y. Okay, I'm going to, let's say put 3 of these samples in training, and you see the scatter plot of this training set here. Is that part clear? You are seeing the scatter plot of the 3 points currently here. Okay, and the remaining 2 parts are the test. Okay, remaining 2 parts are the test, and the test samples are probably here. Okay, the samples are probably here. Now the question is this: you train, you trained a model. So if I make a model, a linear regression model using this data set, let's say I do it like this. This would be the best fit line, right? Because the points are collinear.
Yes.
Yeah.
Okay. So if I show that, okay, this is the line, this is the same line which I'm drawing here. Do you think it does a good job on the test set?
No.
Okay. So what is the fundamental assumption when you are breaking your data into train and test? Think about this. When do you think the model that you learned from the train set will be doing good on the test set? When the distribution of data is almost the same, right?
Yes.
Can I say that the similar samples are present in the test? Does that make sense?
Yes.
Okay. So if you deploy this model directly on the test set, it will not do well, right? But do you think that this model is, isn't this model exceptional on the train set?
Yes.
Okay, let's talk about some more examples. Let's say, maybe say this is the data that I give you. Okay, and this is the train data, and maybe say this is the test data. So if you try to fit the best possible quadratic function, you will probably get like this. Okay, this is the best possible quadratic function. Okay, and let's say if this is the best possible quadratic function, the test points are lying somewhere here. Will it do good on this test set?
No.
No, right? Okay. But what is our ultimate objective? Do we want to do good on the test or the train? What is the final objective when you want to deploy a machine learning model?
Test.
Good on the test.
We want to do it well on the test, right? So the algorithms that you have seen so far, what is it that they are doing? Don't you think they're trying to do well on the train only? They're not trying to do well on the test.
Yes.
When you minimize an error function, okay, let's say yi minus yi hat whole square, don't you think you will reach to this solution which is the best for your, you can say training,
Yeah.
not the best for your test? Okay.
Yeah.
Even when you think about this, don't you think like if you, minimize this, you will reach to this solution, right? You will not reach to a solution which is probably like this. Oh, sorry, which is probably like this. Yes or no? Okay, now I have to ask you something. Please listen to this very, very carefully. Okay, let's say that if you look at this line, can you tell me, let's say this line is L1, this is L2. Which line has more error, L1 or L2?
L2.
L2 has more error, right? So can I say that L2 will actually probably do much better on the test set than L1?
Yes.
Does that make sense? Okay, but L2 has more error, right? So do you think that if I can deliberately add some error in this equation, then I will probably never reach L1? And if I add more error, I might reach to this L3, and maybe L3 is even better on the test examples. So if I keep on adding some penalty instead of calling it some error, let's say I keep on adding some penalty, and now I minimize this thing. Penalty is a positive penalty. See, your goal is to minimize error, right? If I add a positive penalty function to it, so this is the function, okay? It's not a constant that you're adding. Okay, what happens if you add a constant to a function? Let's say you're trying to minimize 3x squared plus 6. I add a constant to it. Okay, I just added this constant 5. Do you think that the root changes?
No.
The
No.
same.
The root is the same, right? I want to
Yeah.
get a different value of MNC. So I will not be adding some 5 here. I'll be adding some function of x. You can call it, I will be adding some function of x now. Okay, which is a positive function. Okay, I'll be adding some function of x now. And now I'll be minimizing this. Okay. So I'm telling you, as long as this gx is positive, okay, do you see that I can reach L2? If I increase more penalty, do you think that I'll reach L3? Yes or no? And I can test on the test set using L1, L2, and L3. Which one is better, right? Yes or no? I can check with no penalty. I can, so maybe see, I multiply this gx with a positive constant called as lambda. So if lambda increases, to which line I will go? L2 or L3? Lambda is also positive.
L3.
L3, right? You will have more error. More error means you are far away from the actual data points. So don't you think for different values of lambda, I can test like which function is better on the test set? Yes or no? So instead of directly reaching to the best solution, I am looking forward to finding that solution which is better on the test set. So what I have done is I have added this penalty function multiplied with a lambda to this. And lambda is also positive, penalty function is also positive. Do you realize that now I can reach to L2 and L3? The solutions which are much, much closer to the best fit line, but they do better on the test set instead of the train set.
Trained.
Does that make sense to you? Is this part
Yeah.
clear? Okay.
Yes.
But like we were adding a penalty means like we were going far away from the actual point so that the error will be increased in the train set, right?
Yes. So see, think of it like this. I am trying to start from initial value. So let's say you're doing gradient descent. Okay. So if I do gradient descent to the fullest, to which line I will actually reach at the last?
The actual.
If there is no penalty, to which line I will reach at the last? L1, right?
Yeah, L1.
Okay. So I'll tell you that you can think in terms of gradient descent also. The idea is this. Let's say this line is far away, right? Okay.
Yeah.
Don't you think if I update it one more time, it will probably be like this?
True.
Then it will probably be like this. Do you think at every step I can decide, okay, where to stop or not?
We can.
I can actually see the error on the test set and I can decide whether to stop gradient descent or not.
Okay, so by increasing the penalty, I can see more improvement in the test set. So
Yes, that will help you decide whether to stop or not. Okay. So see, if there is no penalty, you will directly reach to L1. Okay. Okay. If you think in the reverse direction from gradient descent, I'm trying to move as close as possible to L1. Okay. I'm trying to move as close as possible to L1. But the idea here is maybe L1 doesn't give me the best performance. If it does, that will be the best on the test set, right? If
True.
it does. Okay. So I will test on everything. Okay. I will test on everything.
So for my better understanding, I'm saying like if there is more error in the train set, like the test will perform much better.
Not always. You have to check.
Okay, so I need to check like from the L1, L2, L3. If the L2 was performing more than the L1, I can fix
on the
with
test
L2.
set.
Okay,
Then you can keep L2 and forget about L1. Okay.
Okay.
All right.
So when we were doing the test set is important so that we were giving more importance to the test set instead of train, right?
We always think about the final thing, right? The test set. Our focus is the test set. Okay. See, we also want to learn, right? So we also want to do well on the train set. See, is it that the error on the train set is very high when I'm going to L2 or L3?
No.
Why not this line? I mean, if you look at this line, which is this line L4, do you think this will do good on the test set?
No, probably.
Will be worse on the test set also, right? So you want to learn, right? You want to still be as close as possible to the training points, but not too much so that you try to cram them.
Totally. Okay.
So in the hope that we are still able to do well on the test set, okay? But we don't want to do that well on the train set so that it performs negatively on the test set.
Negatively. Okay.
Okay. So just one phenomenon. So this phenomenon has a terminology called as overfitting. Overfitting is a phenomenon which says that when model performs exceptionally well on your test set or on your train set, okay, when model performs exceptionally well on your train set, okay, on your train set, however, it fails miserably on the test set, okay.
True.
This phenomenon is called as overfitting. You can say that somebody has overlearned, okay. All right. So maybe there was a student who crammed the entire book, but the questions came from beyond the syllabus. Okay. So the guy will fail miserably in the exam. Okay. This phenomenon is called as overfitting. And there is this person, there is another phenomenon called as underfitting. And what underfitting says is that, okay, the person didn't even study the book. Okay. The model fails miserably on the train set also. Okay. So this is like a student who didn't even study at all. So can you tell me which line amongst L1, L2, L3, L4 is underfitting?
L4.
L4. It fails miserably on the train set also. Okay.
True.
All right. Obviously, it will fail miserably on the test also in that case. Okay. So underfitting is the student who doesn't learn. Overfitting is someone who just crams the topics. Okay. Crams the samples. So the thing is, most machine learning models, they overfit. Okay. Most machine learning models, they overfit. I mean, underfitting will happen if I'm not learning, right?
True.
Okay. So think about this. If I give you this type of data set, okay, maybe say this type of data set, I'll just end it quickly. Okay. If I give you this type of data set and you learn, say, a linear model, okay, you learn a linear model, can I say that the linear model will probably underfit? Is it sufficient to model the training set? Think about this first. No, right? So will it give you bad results on the train set? Yes, right? Of course it would. Okay. Yes or no? Of course it would, right? If you think about it. So can I say degree 1 model is not sufficient to learn this type of data? So it would probably underfit. Yes or no? Think. So you can actually figure out, okay, which degree, I mean, okay, let me actually talk about maybe this. Let's say this is how the data looks like. Okay. Do you think a line is sufficient to model this?
No.
Okay. This is actually a degree 3 model, by the way. I mean, the data generated from degree 3. So if I do this, can I say that degree 1 model is not sufficient to model it? It is kind of underfitting. So the test examples will also be like something similar, right? Yes or no? I mean, test examples cannot be far away, right? I mean, we are getting from the same data set only. It will not be exactly like very far away, right? Okay. So in this case, I will still say that degree 1 is underfitting probably. What about degree 2? Can I say degree 2 is still underfitting? So degree 2 would probably be like this. It will still be underfitting, right? You have to reach to degree 3 at least. Okay. You have to reach to degree 3 at least. Okay. So we will discuss this concept of overfitting and underfitting in more detail in tomorrow's class. And we will see how do you avoid overfitting and underfitting. Okay. Okay. Can you tell me how do you avoid underfitting? That is simpler. What would you do?
Like
add more features, get more thetas. Think, if I add one more feature, let's say, so for this curve, can you tell me which degree is sufficient?
3.
3, right? Okay. So I started with degree 1. I will see the results on the test set. If it is worsening, and on the train set also, if the results are bad, I will say it is underfitting. Okay. Then I'll go to degree 2. I will see that probably the results on the train set have improved. However, on the test set, it is still not very good. I'll increase degree 3. On degree 3, what will happen? What do you think? It will actually pass through all the points. So we are in a situation where we are overfitting. So I might have to get another curve, which is still degree 3, but still fairly close to this, which would probably do well on the test set. How to do that? We'll discuss about it. Okay. That is what this regularization is. Okay. Regularization is a technique to avoid cramming of the examples. Okay.
By
So
adding the penalty, like I'll go to
Yes.
the degree 3, but I'll add some penalty so
penalty,
that it
yes.
will bring
So
down.
that it is still a degree 3 function, but it is
But
much
it's
closer.
not actually the degree 3. Okay.
No, it is still degree 3, but you
Okay,
are
okay.
still much closer to it.
True.
Okay. You're still much closer to it.
Okay.
Okay. By the way, okay, this is just my last question. I'll stop with this. Do you think that a degree 4 model, okay, a degree 4 model encompasses degree 3? Okay, if I make, say, a subset of degree 4, do you think it is wise to say that degree 3 model will be a subset of it?
Yes.
Yes, right? Okay. Why? Because let's see this. Let's
Have
talk about, say, degree 1. How do we write degree 1? Can I write it like this? Say bx plus c. This is degree 1, right? How do I write a quadratic equation? Ax square plus bx plus c. Can I say that if I set a to 0, it is nothing but linear?
Yes.
So degree 2, so if degree 3 is sufficient, don't you say that degree 4 would also be sufficient,
Yes.
but not the other way around? If degree 4 is sufficient, degree 3 will not be sufficient. So even if you increase the power of your model beyond degree 3, don't you see that like the model will actually drastically fit to your training points? It will pass through the training points very, very badly. The training error will actually become 0. Okay, we will see that tomorrow. We'll see that tomorrow. So even if you increase the degree beyond a certain level, you are actually putting into more and more state of overfitting. See, maybe there are some points like this here. Do you think that a degree 3 model is sufficient to go with it?
No.
No, right? I mean, it cannot pass through all the points. Okay. But if I keep on increasing the degree, would it happen that I can come up with a function which would be probably like this?
True.
But do you realize this function is not going to give me good results on the test set? Yes or no? So we will see about like how to tackle such problems. If I increase the degree too much, what to do? Okay. So I'm going to show you, even if you increase the degree too much, you don't have to worry about anything. This concept of regularization will help you. Okay, we'll see that.
So like the last thing that you said, like there is a lot of jiggling in the function, right? So this will perform
Badly on the test set.
badly on the test set.
The
Right?
train error is actually 0. Let's say it passes through all the points. So it does exceptionally well on the train set. However, it will do miserably on the test set.
Okay.
Okay. All right.
Fitting. Totally. Okay.
Okay. So we'll see that in tomorrow's class.
And Sanatan, tomorrow, like it's Friday, right? Do we have a class or?
Tomorrow is Friday? No, maybe
Yeah.
then next week. Okay, next week.
Okay. And I just want to ask, like, is there any website or YouTube channel like we can refer? Like, we sure that like we can raise a query and then we learn it, but still, like, if we want to go through and then like to learn up by ourselves.
Okay.
Like,
Do
is
you
there
want to
any-
learn in simple words, or do you want to learn in, say, more mathematical way?
I'll say simple words because I'm not
Okay.
that kind of a mathematical
Okay.
guy.
So no. So my suggestion is, there are some channels which do really well. So there is this channel called as StatQuest.
1 minute.
Okay.
Let me
Okay.
mark it down.
There is this channel called as so see, if you just want to watch video lectures, then I recommend this guy, Andrew NG. He is a professor at Stanford, but he has a course on Coursera where every machine learning topic is described in I mean, not every machine learning topic. He breaks the like one topic into videos of 5 minutes or 8 minutes each.
Okay.
So he'll break it into individual topics. So what you can watch the Coursera videos. Okay. But when he actually teaches at Stanford, every lecture is 1 hour and 45 minutes. So if you
Okay.
want to dive deeper into mathematics, those lectures are also available. Okay. But he has a foundational course on Coursera also, where every topic is broken down into smaller chunks
So
that you can understand easily.
okay, so for the StatQuest is
StatQuest is another it's another YouTube channel. Okay, where this guy his name is Josh Stammer. Okay, this guy posts about different machine learning topics in very, very small videos with good visualizations.
Okay.
Okay, I'm forgetting the name of the guy. Okay, just give me a second. I'll tell you what to refer to.
Okay. And like, is there any Udemy courses that you refer? Because I haven't subscribed to Udemy.
Okay, I frankly, I don't recommend any Udemy,
Udemy.
Unacademy, or
Okay.
any course. Okay.
Okay.
If I want to learn, I will prefer learning from these Ivy League professors.
Sure.
Okay.
Okay.
So I don't do that, but you are
Mhm.
free to do that because they use only the relevant things. That's what the purpose is, right?
Okay.
But if you want to know more in detail, let's say you want to end up as an ML engineer or AI engineer later on, I
Mhm.
will recommend many professors to you that you can watch in your free time.
Okay.
Okay, so I can tell you maybe about a couple of professors that I prefer. So one of the professors, he is called as Nando D. Freitas. He teaches in Columbia University. One more professor is there. His name is Kilian Weinberger. Okay, he is retired right now, but his lectures are available. There is one more professor,
Nando de Freitas and then
Kilian Weinberger. Kilian, Killian Weinberger. I might be misspelling their names like a little bit.
Okay.
Okay, and there is one more. I don't know whether you'll be able to find his YouTube lectures or not. He's an Israeli guy. Just type OpenMIT courseware on YouTube, and you will find his ML lectures. Just type intro to ML. He'll be the first guy that will appear. He's an Israeli guy. I'm unable to pronounce his name. That's I don't want to mess up his name. Okay, this is very
Okay.
bad.
Okay.
He's an
1 minute.
Israeli
Like,
guy. Okay, Omar something. Okay, Israeli guy. Okay.
what I like? Okay. Introduction.
Just
to
type OpenMIT courseware on YouTube. There are
Open-
so those are lectures uploaded by MIT people. Okay, if you want to refer to someone Indian, then I recommend Mitesh Khapra from IIT Madras. And there is one professor from IIT Kharagpur. I don't remember his name. The lectures are available for free on NPTEL. Okay, so Mitesh Khapra is also a good professor. You can watch his lectures. Okay, there is someone from IIT KGP. I don't remember the name. I watched it around 18 years back, so I don't
Okay.
remember the name. Okay.
So yeah.
I mean, those lectures are updated. Okay, it's not that they are 18 years old. So those people keep on updating the lectures like as the time progresses. So you asked for some resources, right?
Yeah.
I believe here I have some resources. These are some
I
of the
think
books. I
this.
think I have uploaded. You have this
Yeah, you
slides,
uploaded
right?
it. Yeah.
These are some YouTube channels that you can refer to here. Okay, his name is Code Emporium. Okay, this is the YouTube. I mean, here you can get a description of all machine learning topics in detail.
Okay.
From Code Emporium. Okay, he is an Indian guy studying probably PhD or MS. Probably he would have finished his MS, but now he is doing his PhD somewhere in the US.
Okay.
Okay.
Sure.
Okay.
Because like when it comes to Max, like it's been 7 years since I haven't done anything. So that's what
Don't worry. Okay. I mean, if you are interested in just learning the maths, there is one more book that I'll refer you. This is called as Mathematics for Machine Learning, and the authors are Aldo and Fazil. Okay, I don't remember their first names, but these are the surnames. You can find this book for free on Google. The very first link, if you just type this, you'll get the book link, a PDF of it.
Okay, so that is the that will be the mathematics and everything.
Mathematics. So everything that you want to see about ML, linear algebra, calculus, all those necessary details, they are there in this book. But it's somewhat advanced. Okay. But if you want to just learn the basics of like the mathematics that are used in ML, everything is there in this book. If you want to learn, let's say, implementation specific ML, so there is another book which is Machine Learning with Python, something like this, and the authors are Sara Guido and Andreas Müller. Okay, this is for Python. Okay, using machine learning with Python.
Okay, the book name is Using Machine Learning with Python, right?
Something like ML with Python, I believe it is. ML with Python or machine learning with Python. I think something like that. It's a I think it's Pearson's publication probably. But if you type the name, you'll definitely get the book. Just type it on Google, you will probably get it.
Sara Guido, okay. Sara
Guido and Andreas Müller. I think they are French people.
Okay.
So it's a good book. It's a good read. I have this book. Probably I can. I mean, I have it in my my closet in my house. I'll share it if you want. Okay, you can find the copy online also.
Okay.
It's easily available. I think some guy would have hosted it for sure. It's a good book. Okay. It's probably Pearson's or I believe it's Pearson's only, if someone can check online. So you can refer to all the implementations in this book. Very good book.
we can, like very first link will was giving the PDFs, which you
Yeah,
are
yeah. So you
saying.
can, so that's why I said like these books are very popular. So you just download them and refer to them whenever you want. Okay.
Sure.
So what I'm teaching you
Okay,
right now is
Sanatan,
an
thank you.
assimilation of all these things.
Okay. Yeah,
All right.
sometimes like I'll just go blank. So that time these things will help. So that's what I've asked.
Sure. Take your time to go through these. And when we meet the next time, I believe on Monday now, we'll discuss this concepts of regularization. And then we will start implementing everything.
Sure.
After
Sanatan.
regularization, no theory about linear regression will be done.
Okay.
Okay. So next 2 sessions probably would be about implementation.
Sure.
Any other questions? Anyone who has any questions? So if you are still finding maths to be difficult, my suggestion is utilize the next 2-3 days. Maybe rewatch the video lectures, and wherever you get stuck, try to search on Google, try to understand maybe an alternate way of, going through that topic. And see if you are able to learn that. If not, then I'm here. You can reach out to me in the next class. And don't worry about about any extra classes. Don't think about what others are. Others will judge you or not. Okay. Don't worry about that. Nobody knows you. Even I don't know you. Okay. So don't worry about like what others will think about you or anything. Ask and as many times. We will not be friends, right? Yes or no? All of us, we are acquaintances right now. We'll become friends if you meet me in person and probably spend some time with me, and it will progress, right? So don't think about if other people are judging you or not. Utilize your time. You have paid for it. That's why I keep on asking. Ask as many times as you want. You have, you have paid for it. Okay. Don't let it go to waste. Don't be shy. If you are an introvert, you will probably not succeed. That's what I feel. Okay, that's what I feel, but may not be true. Okay, may not be true. So, come out of your shell and ask as many questions. It's not the university setting anymore, or a class setting where you are in a class setting with many people. And if you ask a silly question, trust me, no question is silly. Also, no question is silly. Okay. Because the question that you may have, others may also have, but they are shy to ask. Okay, so ask as many, because it can raise even good things for me as well. I will then search. If I don't know the answer, I'll get back to you in the next class. I'm not, an oracle either. Okay, I don't know everything. So I will not know the answers to some things, and if I don't know, then I'll teach you in the next class. All right. Okay.
Sure, Sanatan.
So take care, guys. We'll meet now on Monday, and if you find anything, okay, I've already shared my email ID. You can write to me. I'll respond maybe within half an hour. Okay. If I'm not taking a lecture, then you would probably have a response from me in maybe 10 minutes. Okay. But please do it if you have spent some time on it. If you just write to me like directly, and if I find it trivial, I will not even respond. Okay. I'll be frank about it. Okay. If it is very trivial, if somebody can get the answer just by typing it, I'll not respond to it. Okay. If you ask me for a resource, then I'll share it. Okay.
Okay.
All right, guys. Take care. Bye-bye.
Yeah. Thank you, Sanatan. Happy weekend.
You too. Take care. Yeah.
Bye.
Bye, everyone.